Okay, energy level diagrams. So the idea with these energy level diagrams is they're just a nice graphical way to show the different electrons that exist in an atom in a way that reflects the energy associated with the orbits of the electrons that the electrons exist in. So let's just give ourselves an atom to talk about. Let's talk about oxygen. Oxygen has 8 protons, 8 neutrons, and 8 electrons, if we're going to assume it's neutral. So we're focused on the 8 electrons here, and we're going to figure out where they're going to go according to these new orbitals. So we can make our electron configuration for oxygen. We can say that the first 2 electrons go into the 1s2 shell. The next 2 electrons will go into the 2s2 shell. And the third set of electrons will go into the 2p shells. Now, if I want to be really specific, I can say px, py, and pz. And when I fill electrons in these shells, I should always go 1, 1, 1, and then 2, 2, 2 as needed. In this case, I need 4 more electrons, so I go 1, 1, 1, 2, and I end up with 4 electrons. So I could write px2, py1, pz1, but I can also do a shorthand notation where I simply write P4, understanding that I put 1 electron in each orbit first before filling the second shell. Let's look at what that looks like in an electron or an energy level diagram. For an energy level diagram, we start at the bottom, 1s, and we'd use arrows to indicate the electrons. So that would be a full 1s shell where I've shown one arrow with a spin up and another arrow with a spin down. Then I can add the 2s shell, and again I can put one arrow up, one arrow down because it's full. And then I'm going to get up to my 2p shell, and usually I will put these off to the side a little bit, just sort of like tabbed over one. I put 3 orbits to represent the 3 possible p shells, and then when I put in my electrons I go 1, 2, 3, putting 1 electron in each cell, and since I need 1 more, 4. I always put 1 electron in each cell as opposed to pairing them in the first place, because that's how they would really behave in the atom, recognizing that while these electrons are pretty good at not seeing each other, when they do see each other, there is still some electron-electron repulsion. So that's our energy level diagram for oxygen. What I can see from this energy level diagram is I can see 2 clear spots where if I wanted to make oxygen into its typical stable ion, I can see how I could add, where I would add 2 electrons, or I could form 2 bonds to other things to make an or to make a molecule. So that's one of the ways we use energy level diagrams. Let's go now and do something larger. Let's do something like zinc. And zinc, let me just look it up here. Zinc, actually, oh, well, whatever, I'm there now. No, you know what, I'm not going to do zinc because I want to illustrate something else. I'm going to do chromium. Why not chromium? Okay, chromium has an atomic number of 24. So we're going to deal with neutral chromium, which will have 24 electrons. And we're not going to worry about the number of neutrons because we're just doing an energy level diagram that's going to show us the location of our electrons. So first things first, I'm going to do the electron configuration for this over here. 1s2, that's my first 2 electrons. 2s2, I'm up to 4 electrons. 2p6, so now I have 2, 4, 6, 8, 10 electrons. 3s fills next, 3s2, so I'm at 12 electrons. 3p6, so what am I at? 10, 18 electrons. I need more. Now this, if we'll recall our rule from a previous video, is where something strange happens. We might think the 3D should be the next shell filled, but the angular momentum associated with that shell makes it actually higher energy than the 4s shell. So we get the 3D shell, 3D, and here we're going to get how many left? 2, 4, 10, 12, 18, and I have 24, so I have 6 electrons left. And that shell can hold up to 10, so 6 is fine with it. I showed you how to write the orientations for the p orbitals, and that's useful for us to have some way of discussing them px, py, pz, but I don't want you to spend the time to memorize the designations for the orientations of the d orbitals. So you can look at them online, they're x squareds and y squareds and whatever, but don't bother spending any time trying to learn those because it's not important, at least not at this time. So now let's make these energy level diagrams, 1s, 2s, 2p. These are all inner shells, and they're all going to be full. 3s, 3p. Now we're going to get our 4s and our 3d. So for d's, again, we're going to go over one more space to designate that they're different. And here we're going to include 5 possible locations because there are 5 different orientations for that shell, making room for the 10 possible electrons. Here I'm going to go 1, 2, 1, 2. I must have done some math wrong here because I should have ended up with... Hold on a second. I see what I did. Okay. When I said that there were 6 electrons left for this, I forgot. I just did all this stuff to say that the 4s shell comes in next, but I didn't actually put it into my electron configuration. So 4s2 should have come next, and then my 3d should have been 3d4, not 3d6. That makes more sense. Sorry, I realized I made a mistake because I wanted to give you an illustration of when the 3d shell doesn't have paired electrons, so that I can make the point that you only put 1 in each shell, so I nearly missed that. Anyway, 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then 3d, 4 left over. Anyway. Okay, so continuing filling, my p's are full, my 2p's are full, my 3s is full, my 3p is full. My 4s gets its 2 electrons, and then my 3d gets 1, 2, 3, 4. Now, this is a little bit confusing because you're looking at this and you're seeing all this open space and you might think that that's opportunity for bonding. But the problem is, from a chemical bonding perspective, while this is lower energy, it's still larger. So when another atom approaches it, while these are higher energy, the fact that they're smaller means atoms see these electrons first, other atoms. Which means that despite the fact that it looks like there's open space here and that there could be some complex bonding that can go on, it's actually these electrons that will be involved in forming chemical bonds. Now, is it possible for an atom to lose these 2 electrons and then start doing bonding with those other electrons? It's possible, but the first thing that's going to happen is that it's going to lose these 4s electrons, and so the primary way it's going to bond is using those 4s electrons. So that's our energy level diagram. That's how we can use it to understand what's going on with the atom. And interestingly, that's why chromium, despite the fact that it looks like it has a whole bunch of electrons that could be involved in complex bonding, still primarily behaves as a metal that forms the ion chromium 2+, because the main way that it's going to bond is by losing these 2 electrons and taking on that positive 2 charge. So that's a video on energy level diagrams. Sorry about the little confusion here, but it still shows you how to do them and why it's a useful way to represent the atom. We're going to do more videos on this involving Lewis structures to show you some actual examples of bonding based on the energy level diagrams.